Hello, welcome back. All right, this is our Physics Week 3 lab, Gauss's Law. I think it's the last portion. All right, so in the figure, a hollow hemisphere is in a uniform electric field of magnitude E equals 3 millinewtons per coulomb. The circular rim has a radius of 12 centimeters, is a line perpendicular to the field. Find the electric flux through the hemisphere. As much as I hold the prior questions in disdain, this one is almost reasonable. All right. So this, they say this is 12 centimeters. I'm going to call it 0.12, and that's for meters. So find the electric flux through the hemisphere. Okay. So the equation we're going to use here is flux equals Q enclosed over epsilon naught equals E dot dA. This is completely useless because we don't have a closed surface here. It is specifically open on one side, therefore it's not closed. So nope, this is not, but we do know that flux in a more general sense will be E dot dA. So this is what we're going to use. Integral. So the idea here is all the flux that enters from this side, because the dot product is going to be difficult on this circle here, because if we draw a tangent plane here, this will give us the dA, and then we got some sort of theta right here. Well, we have a different theta here, which this theta will be, this theta right here will equal 0. There'll be another theta down here, and there'll be another theta up here. So there's an infinite number of angles between the electric field and the area. So we really can't simplify that. But we know that all the flux that enters from one side has to exit the other side. And we got a nice flat circle on this side, which we are going to use to calculate. So we're going to find the flux leaving, and we know that will have to be the opposite of the flux it just entered. I say opposite because the signs will be opposite. The magnitude of the flux will be the same. All right, so the electric field will be constant, then we'll pull out the electric field. This then will just be the area of the circle. So we're going to have, what is it, 3 millinewtons? Why do they use millinewtons? 3 times 10 to the negative third times, we're going to do 12 times 10 to the negative second squared and pi. That's pi r squared. So we're going to have 144 times 3. 144 times 3. I could probably do 432. 432 pi. This will be 10 to the negative fourth, 10 to the negative seventh. 10 to the negative seventh. Okay. 10 to the negative fourth, 10 to the negative seventh. I'm going to say that I'm just going to leave the pi in there because I'm like, well, it'll be more accurate. It's not. I'm just too lazy to calculate that in. So that's where I'm going with that one. And part 2. Part 2. In each case, a conductor with cavities is shown in cross-section along with some point charges. The net charge of the conductor, Q cond, is given. Determine the amount of charge on all surfaces inside and outside and sketch the charge distribution on all surfaces. Okay. Amount of charge. Okay. Okay. I keep saying okay, like every time I say it, it adds some value. It doesn't. I could have just said it once. I would have been good with that. Okay. 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 So the entire, I'm going to say entire purpose of a conductor. In a conductor, electrons flow freely. And as a result, electrons are going to arrange themselves so that there are positively charged sections and negatively charged sections. And what that will do is it'll ensure that there is no electric field inside the conductor. Because if there was an electric field in the conductor, it would continually be pushing charges from one side to the other. And the idea is if it's in equilibrium, then there's no charges. There's no electric field. There's no electric field pushing charges, because if there's an electric field pushing charges, then it'd be continually changing the electric field, because charges would be moving. So the lesson learned here is conductors ensure that there is no electric field, no net electric field inside the conductor. So one of the way I draw this then, reduce the brush size down a bit, not too crazy, there we go, that's probably good, is, I think I'll use red too, just to contrast here with the blue. So if we have a negative charge inside this cavity, there's going to be a bunch of positive charges with a total value, when you add up all the plus charges, of plus Q. So then if you look at this from a point of Gaussian, like a Gaussian sphere, so we'll draw a Gaussian sphere around this cavity right here. And we know from Gauss's law that we have flux equals Q enclosed over epsilon naught equals some integral thingy, an electric field, and dA. So what this is saying then is we got positive Q here, negative Q here, you add them together and you get 0. Or at least, yes, negative 1 plus 1 is 0. Therefore Q enclosed is 0, therefore the electric field at this point inside the conductor will also be 0. Okay, so as a quick, so you don't have to think about all that in general, just know that if you have negative here, it's going to attract positive charges. Specifically, it's going to attract exactly the opposite to make it neutral. So negative Q there. We are then going to have charges here. Since it's a smaller cavity, it's going to have a higher density, but it's going to even out so that the total charges on the outside here are exactly positive Q. That way, when we do a Gaussian surface around this cavity, it also becomes 0 Q enclosed. All right, then we have, I think, a total overall charge of negative Q. Now we need to find out what is going to be the charges on the outside of the sphere. So looking at this, we have a total of negative Q charges to work with. So the conductor has negative Q worth of charge. It lost a positive charge to surround one negative Q, and it lost another positive charge to surround the other negative Q. So we started with negative 1 Q, and we lost 2 more Qs. So the charge is going to be on the outside will be negative 3 Qs. So we'll have negative 3 Qs worth of charges on the outside here. And they will not be completely uniformly. Probably be a couple more here, because there's the positive charges there and they'll try and bunch up towards it. Over here, I drew the positive charges here uniformly. It would not actually be uniform. So they will not be uniform. They'll actually bunch up here, and then there'll be fewer on this side over here. That way, it will cancel it out better. Cancel out the electric field from the charge inside the cavity. Okay, let's see if we answered all the questions we had for this guy. Net charge, determine the amount of charge on all surfaces inside and out, and sketch the charge distribution. Okay, I think that would be true. All right, looking at the next one. So we have negative 2 Q here, so we're going to have 2 Qs worth of positives on this side right here, and then they're going to be clumped or clustered more towards the negative 2 Q side. All right, so we have 5 Qs here, but we lost 2 of the positive Qs due to canceling out the electric field from the negative 2q charge inside the cavity. So what we're going to be left with is 3 q's. And then, so let's see, now we need to determine what the distribution is going to be. So we're going to have more positive q's over here, but they're going to be, those are going to be there and canceled out by the negative 2q. So I'm going to say we have a uniform charge distribution. Yes, we'll have a uniform charge distribution. This one, I think we're going to actually have more negatives here because the cavity is not centered. This one, the cavity is centered, and then even though this is not giving off a centered electric field, the electric field that's using to cancel out is not centered either, and it's not centered in just such a way that it will cancel out the uncentricity of the charge. So as long as the cavity is centered, that's all that matters. Okay? Now this guy, so we have negative 2q, so we'll start on the inside, work our way out, where we'll have a larger cluster over here, and we'll have 2q worth of positive here. Now for here, so we have negative 4q, and we lost 2 q's worth of positive, so we have negative 6 q's to work with over here. And these negative 6 q's will try to avoid the negative 2q up there. I don't think they'll avoid it in a perfect there'll be some sort of distribution like this where we'll have more on this side and fewer on this side. Okay? So the way to do these is you first look at what your charge is in the cavity, and you set up your charges around it of the same magnitude, and then a distribution based on where the charge is located to cancel out the charge on the inside. You then find out how many charges you have in all the cavities, and you subtract the number of induced charges, these guys, that you had to move from the conductor to offset the electric field created inside the cavity. And after you subtracted those, then you know how many charges you have to work with on the outside. And then you distribute those as evenly as you can. Okay, find the electric field in all space due to a uniform solid sphere of charge of radius r and volume charge density rho. Give your answer for the magnitude in the form of the equation E equals this, where r is the distance from the center of the sphere. The easiest way to specify the direction is in words. Note that the charge divides space into regions. You'll need to supply a separate answer for each region. Wow, I did not understand most of that. All right, so you need to find the electric field in all space to a uniform solid sphere. Okay, I see what we're going here. And they want real answers. Real answers. So difficult. Why is this one part of the problem harder than all the other parts combined? Okay. So we have our sphere. Probably don't need that sphere. Okay. So we have various regions. Excuse me. We're going to have the regions inside the sphere and outside the sphere. So I'm going to start by writing up what rho is. Rho is dq per d volume. And I'm going to write up Gauss's law, which is flux equals q enclosed over epsilon naught equals double integral surface E dot dA. Okay? So the first region we're going to start with is the exact center. E at r equals 0 equals 0. Bam! Easy one done. All right, so now we're going to do it for an area inside the sphere. So Q enclosed for r is less than r will equal 4/3 pi r cubed, which is the volume of the sphere on the inside, times rho. And looking at it intuitively, rho is dq dv. We multiply by a volume, which is the volume. We're just going to be left with a q. So that'd be q enclosed. We know what epsilon naught is, and then we know the area will be, so draw double integral dA. This will be the area of our sphere. It'll be 4 pi r squared. Okay? So putting it all together, we will then have electric field R, where R is less than R, equals Q enclosed, which is 4/3 pi r cubed rho, over epsilon naught, and then we're going to bring this guy over there, 4 pi r squared. So these r squared cancels out 2 of those r's. I'm going to leave the, yeah, I'll get rid of these guys. 4 pi, and we are left with rho over 3 epsilon naught. And we have an r up here. Yep. All right, so then the next region will be where r is greater than r. I know that doesn't make sense, but little r is bigger than big R, which still doesn't actually make sense. All right. So I'm going to then treat everything as a point charge. So I'm going to use, I'm going to write up Gauss's law, because that's what we do every time. Q enclosed over epsilon naught equals double integral E dot dA. There we go. Where Q enclosed this time is going to be 4/3 pi r cubed, where it's big R, times rho. The integral dA will this time be 4 pi r squared, little r squared, which is actually the bigger of the two r's. And then we can then simplify using math. Move this guy over here. First thing we do is we pull the e out, and then we do that. So Q enclosed would be 4/3 pi r cubed times rho over 4 pi r squared epsilon naught. Yep. And those are the 3 regions, and then they ask for a direction. The easiest way to specify the direction is in words. So I will say the direction of the electric field is outward. I think it's interesting that they said to use words, and I used word. Yeah, no, never mind, that was a terrible, terrible pun. Now the charge divides spaces into regions. You'll need to supply a separate answer for each region. All right, so I gave 3 regions: 0, inside the sphere, and outside the sphere. And since it's positive, the electric field will start here and go outward. Yep. And we already did a couple of those, I believe, in the homework, so it should make sense to you. Uses Gauss's law to find the electric field in all space due to a thick, infinitely long cylindrical shell of charge with volume charge density negative rho. The shell has inner and outer radius of A and B. Thick, infinitely long cylinder. Okay? So I'm going to draw this as 2 concentric circles because I'm going to be looking at it head on. There we go. And then it goes off that way forever. And even though I said forever, I just drew the end right there. Okay, I'm going to say they can't see it because it's, perfectly lined up. Infinitely long cylindrical shell, and this time we have a negative rho. Okay, so we're going to be using Gauss's law again, partly because they told us to, and partly because it's just a good idea. So Gauss's law, we have flux equals Q enclosed over epsilon naught equals E dot dA. Okay, and then since we're going to be measuring it out radially outward, we can pull the E out. So then Q enclosed will be related to so it wasn't very specific. So use Gauss's law to find an infinitely long cylindrical shell. All right, so this is A and that's B. So I'm going to say for R less than A, electric field equals 0. And that's because at that point there will be 0 Q enclosed. So then Q enclosed for when it's not, when an AR is bigger than A but less than B, Q enclosed will be, so the volume will be pi R squared minus pi A squared times whatever length of the cylinder is times rho, which will be negative. All right, you're like, what would you just do right there? Well, looking at it this way, zoom in a lot, excessively. So what I did then was, if I want to find this area right here, I found the area of this whole circle on the outside, and where this is, get some red, where this right here is R, and I subtracted the area of the circle, R is supposed to go all the way bottom, on the inside, which is area A. And that's what I did mathematically right there. R squared minus A squared. Yep, and since R is bigger than A, we'll get a positive number, which is what we want. Okay? And then everything else seems pretty, oh, we need to do area, dA. So the area, ooh, now I have red, will be 2 pi r, which will be the circumference of the circle at r. The circumference of this circle here, where r is bigger than a, but less than big R. 2 pi r times L, which will be the length of the infinite cylinder. So since L is infinite, I'm kind of worried, but hopefully that problem will just work itself out. All right. So rewriting this, we have Q enclosed up here, which will be pi r squared minus pi a squared. I could probably factor out a pi. I'm not going to. When given a choice in life, I take as much pi as I can. Times L divided by epsilon naught. I'm going to divide then by this portion right here, which will be 2 pi r L. This guy cancels. That guy cancels. Can't cancel the r's because there's this minus pi a squared involved. Probably can cancel the pi's. Man, I just ruined by maximizing pi rule for life. Oh well. So we have r squared minus a squared. Actually, I'm going to do something overly clever and not useful. Rho times a squared minus r squared. Yeah, see, I just distributed the negative there. Clever, clever, not useful. Epsilon naught, if anything, it reduces understanding, times r. Okay? And that will then equal the electric field. And in the direction, I'm not going to even look at it. If you look at the equation, you know that a squared is going to be less than r squared, therefore it's going to be negative, but just intuitively know it's made out of negative rho, negative charge. Therefore, the direction will be inward. All right, so now we have one more region to cover, and that is when little r is bigger than big R. So we're going to do the exact same idea here, except this time Q enclosed will be pi big R squared times length times rho. And there'll still be the negative in there. And then dA will still be the same formula. This time R is bigger, so it will be a different value, but the formula for the dA will still be 2 pi RL. So then we'll have the electric field equals, look up here real quick so I can look at my Gauss's law. Q enclosed, which will be pi R squared L times negative rho over epsilon naught, can't forget that guy. And let's see, what else do we have then? We have the area, which is this guy right here, 2 pi RL. 2 pi RL, pi's cancel again. One of the, ooh. No, that R still stays there, and this is the wrong R. That has to be big R, because the Q enclosed, once we get past the outer radius, like, that's all we have. I still need to subtract a squared though. Okay, I'm going to redo that slightly. Because that was saying I had a solid cylinder. So this will still be pi R, big R squared minus pi a squared. There we go. Times L times negative rho. All right, let's try this again. Take 2. Cross out. Equals. That was a terrible equals. All right, now take 2. So we have pi a squared minus pi big R squared. Again, just distributed the sign. L rho over epsilon naught 2 pi R times L. Cancel out, and there you go. That's a times, not a negative. Yep, and then it'll again be inward. I guess we just switched the little r and the big R for that one. Nice. Yep, I think we did well on that. We did well on that. I'd go into more detail with that normally, except we've already done a million of those like that on the homework. So if you haven't watched the homework videos, you should watch the homework videos. All right, number 5. Use Gauss's law to find the electric field in all space due to a thick, infinitely wide slab of charge of thickness T and volume density negative rho. All space, that means they have to contain, okay. Okay. So this is going to be our infinite slab. There we go. And the Gaussian, so what it's going to do is it's going to create a uniform electric field going this way. Or, nope, actually, it's negative. So it's going to be going into it, like this. Then from the bottom, it's going to be going up like this. So what I'm going to do is I'm going to use a cylinder for my Gaussian shape. God, it feels kind of like a Pokemon. It's like, what kind of Gaussian shape are you going to use for this fight? I choose you, cylinder. Use Gauss's law to find the electric field in all space to a thick, infinitely wide slab of charge of thickness T. Aha. Probably a Mr. T joke in there. And volume charge density negative rho. All right. So I have no idea what to do. So we're going to start with Gauss's law. So flux equals Q enclosed over epsilon naught, which equals integral E dot dA. Okay? So dA here that we're going to be concerned about here is all the flux that's going up through here. So the only area we're going to concern ourselves with is this area right here. Your thought might be like, but why don't you care about the area on the side of the cylinder? Well, here, the dA, the small segment of surface area, I don't know why I have so much trouble remembering that, and the electric field are perpendicular to each other. So the theta will be 90 degrees. So cosine of 90 degrees is 0. So I'm going to say, yes, I count it. I'm going to count all of them, but they're all going to be zeros. They don't matter. So the only surface area that I'm going to care about is the top and the bottom. All right, so now I need to find Q enclosed. So let's start by saying that, and I'll call this the length, height, length. So I'm going to draw a side view. There we go. Where we have a cylinder. So the first cylinder, I'm going to say, is actually inside it, inside the slab. I'm going to say, so I'm going to call this the height right here. Call this L. I'm going to say for L less than half the thickness, because I just want to center it. I don't know if it matters if I center it. I just feel better in life when things are centered. Maybe it's OCD, maybe it's, I don't know. Playing it safe. So Q enclosed will then be, so we have to find the volume here. So that'll be pi r squared. I'm going to just say we have this r here, right there. And I'm going to hope it cancels out, because if it doesn't, I'm going to be in trouble. Yeah, I hope it cancels out. Pi r squared times 2L, because you have half on top, half on bottom. Yeah, I'm good at that. Yeah, okay. That's fine. I'm good with this. 2L times rho. And is it negative or positive? They just hit negative. Okay. I'll try and keep the negative in there. I'll probably forget it at some point. So let's see here. We got a volume times a charge density. Yes, which gives us charge. Got it. Epsilon naught, that's easy. We got that. And I'm going to rewrite this guy real quick to be E times the integral dA. So that's going to be the surface area. I'm not going to find the surface area of the entire cylinder. I'm just going to find the surface area of the top and the bottom as described earlier. So for here, surface area, dA is going to equal pi r squared times 2, because there's a top and a bottom. Okay? So now with this then, I'm going to say, rearrange an electric field equals Q enclosed, pi r squared times 2L times negative rho over epsilon naught. Yep, can't forget that guy. The area, which is this guy, pi r squared times 2. So cancel, 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 cancel. This seems to be working out well. So we have negative rho times L over epsilon naught. And this is for L is less than half the thickness, where L is the measure from the center upward. And this would be the, we're supposed to find it, use guys have space due to thick, infinitely wide slab. Okay? Where L is the distance from the center of the slab to wherever. In this case, not outside the slab. Okay? Now we're going to do the exact same thing, but we're going to say now that L is greater than T over 2. So again, that was not the right way to draw a flux. Let's see, did we answer it? Yes. And then you can also say that, at 0 it also equals 0. Flux equals, let's rearrange this guy, Q enclosed over, what, epsilon naught? No, there we go. Do some integral lines, some dA, and let's see where we go here. So Q enclosed, well this time it's going to be pi r squared, because that's the area of the cylinder, but it's going to be now limited by the thickness of the slab. So pi r squared times T, and then that's the volume, so we'll also need multiply by rho, where rho is the volumetric charge density. You have a volumetric charge density, multiply by volume, and you get a density. Okay? dA, even though the cylinder is now much, much larger, the sides don't count. So only the tops matter, so we're going to do, again, pi r squared. I could do, did I put length on the other one? I don't think I did I? Nope, just pi r squared. Okay. Right. The length mattered in the previous problem because the more length we had, the more charge we encompassed. And this time, our charge is limited by the thickness of the slab, not by the length of the Gaussian cylinder that we chose. Okay? So now, ooh, but there's a top and a bottom. There's a negative. Did I forget the negative too? Yep, I got it. It's negatives in there. Okay. So dA, there should be a top and a bottom, so multiply by 2. Okay? So then an electric field will be Q enclosed, which will be pi r squared times the thickness times the negative rho over epsilon naught pi r squared and a 2. Pi r squareds cancel. Huzzah. And we're left with negative rho t over 2 epsilon naught. Yeah, that's good. You should probably memorize that result. Not from here, look it up in some other sources too, just to verify. Yeah. I'm always right, but just in case I'm not, you should check just to be sure. Because infinite planes tend to come out from time to time. And this is for L greater than half the thickness, because I imagine that the center of the Gaussian cylinder starts in the middle, and we're measuring from the center out. And I think that's all we got for that guy. Yes, yes it is. I think I chose a cylinder, but I think you could have also used like a rectangular prism, a cube, if you will. I could have used a cube as well. But I think cylinder is probably the classic for that one, and that's what I chose. Okay, that's how you do this lab. Enjoy. Good luck on the homework, and I will see you next time.